Be going over the multiple choice questions for this review. It is going to be a longer video, so don't feel like you need to watch it all at once. You can try to watch it in pieces. This test is going to be over chapters 2 through 6. There's a Kahoot that you have done or will do that helps you practice some of these concepts. And you'll notice that these are all questions from previous AP exams. So it will be very challenging, but don't be discouraged. All right, we're going to do our best to try to learn as much as we can about these concepts before your test. All right, so here we go. The first question, we have a histogram, all right, for 175 patients in a dentist's office, and it wants to know which of the answers could be the median. All right, well, you guys should know at this point that the median is the middle number. So if we were to order all of these numbers from least to greatest for the waiting times, we would find the number that's right in the middle. All right, now, unfortunately, we have a histogram. We don't actually have all of the data values, but I'm going to show you a cool little algebra trick that'll help you find where the median is going to be. So the first thing you want to do is divide 175, that's the total number of data values, by 2. And when you do that, you get the 87.5th data value. Now, there's not 0.5th of the data value, so you always want to round this up to the 88th data value in this case. All right. So I'm looking for the 88th data value, and that's going to give me the median. Now, if you look at the histogram, the first bin is from 0 to 5, right? Right here is 0 to 5, and that's 80. So the first 80 data values are 0 to 5, all right? And we have not hit our 88th yet. But if we go to the next one, which looks like it's about 50, we'll have now gone to our 88th one, right? 80 plus 50 is 130. So that means our 88th data value, I don't know what it is, but it's somewhere between 5 and 10. So when I look at my answer choices, the answer for which could be the median has to be between 5 and 10 minutes. And the only answer that's between 5 and 10 is 7.25 minutes. All right, so that's kind of a cool trick to find the median if you don't have the data values, but you know the total number of data values and you have a histogram. Let's try another one similar to that. Okay, so in number 2, it says we have heights in inches for 200 graduating seniors from Washington High School in this frequency table. It says which of these statements is true about the median. All right, so it's kind of like what we just did. All right, a little different because we don't have a histogram, but we really do have it. We have the bins, which don't have the actual graphical display. So we have 200 divided by 2, like we did before, is 100. So we're looking for the 100th. And when you get an even number, I should say this, when you get an even number, all right, not the decimal, you're looking for the 100th and the 101st data value. Because again, if you have an even number of data values, it's going to have to be the average of the 100th and the 101st. So there's always some kind of either rounding or you go up 1. It shouldn't really come into play. Like as long as you know how to divide by 2 and find that number, you should be fine with these questions. So if I look at my frequency, height below 60 inches is 22. So I have not hit 100 and 101 yet. But when I go to the next one, right, 84, 22 plus 84 is going to be 106. So I've already gone past 100 and 101, right? So my 100th and 101st data values are in this bin, right? They're in this bin. Now, I know you might be confused, but there's only 84. Yes, but because there were 22 before that, when you add the 84, you go past the 100 and 101st, okay? So for my answer choices, I'm looking for the one that is that bin for greater than 60 inches, but less than 66 inches, which is, looks like this letter D. All right. All right. Let's keep going. Number 3. Number 3 says the amount of time required for each of 100 mice to navigate through a maze was recorded. Here's the histogram. Which one is closest to the standard deviation? Now, this one is not really a trick like before with the median about using some algebra. There is not really a way to do this besides understanding what standard deviation is and how to look at the histogram. Now, the first thing I notice about this histogram is the center looks to be around 90, right? So if I'm thinking that the center, the mean, is about 90, right? And I look how far away the data values are from their data values to 90, all right? So if I look at letter A says the standard deviation is 2.5 seconds, right? We've been talking in this past week about the normal model, All right. And your understanding of the normal model at this point should hopefully be that we're going to think about z-scores that are all the way to +3 and z-scores to -3. All right. Anything past that is really not going to happen. Right. This is that idea of the 68, 95, 99.7 rule. So if we find z-scores past 3 or -3, that's going to be unusual. So when I think about this question, I think about if I were to take these standard deviations and multiply them times 3. Right? If I multiply that by 3, I get 7.5 seconds. Okay? So if I were to go from 90 and add 7.5, and from 90 and subtract 7.5, I should really get to like the end of my data values. But if I do that, I only get up to 97.5, which is like up here, and I get down to 82.5, which is down here. Right? You'll notice there's a lot more data values that are past those. So 2.5 seconds is just too small. If I do the same thought process for letter B, that'll be about 30 seconds. All right, 90 plus 30 is about 120, and then 90 minus 30 is 60. All right, so it's not perfect, but you can see that makes more sense to me in terms of a standard deviation in this type of problem. If I try 20 and 50 and 90, those are going to be much too large, and it's going to show way too much spread as opposed to what's in this actual histogram. So the only answer choice that actually makes sense for the standard deviation here is letter B. Okay, let's keep going. Number 4. Number 4 says, which of the following statements must be true about data set A and B if you're given these histograms? Now, a lot of students like to pick either A, B, or C. They're saying the mean of the data sets are the same, the medians are the same, and the ranges are the same. Because they look at it and see, oh yeah, we're going from 10 to 60, 10 to 60. We have our mean or median is in the middle. But here's the deal, guys. I don't actually know what the data values are. So even though you might think, oh yeah, those all sound good, they don't actually technically have to have the same numbers. So there's no way I could possibly know if they're equal or not. They could be, but when I see this must be true, I have to rule those out. Like they could be true, but they don't have to be true. So it really comes down to D and E, right, about the standard deviation. So your understanding, hopefully, of the standard deviation is that it measures the average deviation, so the average distance of your data values to the mean. Let's assume that the average of these two is about the same, somewhere around 35. If they have roughly the same average, you can see because of this large bin here, right, in the center, and it gets smaller as you move away in data set B, that there are more data values that are clustered around the mean. So that's going to have a smaller standard deviation than data set A, which has more data values far away from the mean. All right, so the data set A standard deviation is going to be much larger, maybe not much. It's definitely going to be larger than data set B. All right, so I'm looking for the answer choice that states that the standard deviation for data set A is greater than the standard deviation for data set B. All right, so we look at these. It looks like that's letter E. All right, let's keep going. Number 5. Of the following dot plots, which represents the set of data that has the greatest standard deviation? This problem is why I chose this problem. It's very similar to number 4, right? If the idea is that all of these data values have a similar mean around the middle here of 5, right? If the mean is similar on all 5 of them, we're looking for the one that has the most data values the farthest away from the mean, all right? So when I look at this, that has the most data values the farthest away from the mean, that's letter B, right? That has the most data values that are as far away as possible as they can get from the center. Okay, number 6. It says height in meters is measured for each person in a sample. After they collect the data, all the measurements are converted from meters to centimeters by multiplying each measurement by 100. So which of the following statistics will remain the same for both units of measure? So in the notes, in the lecture about the notes from chapter 6, at the very beginning, I mentioned that if you multiply all of your data values by a number, that's going to change both measures of spread, I should say center first, and spread, right? So any measure of center and spread is going to be changed because of this multiplying by 100. So the mean is going to change, The median is going to change. Those are both measures of center. The standard deviation is going to change. That's a measure of spread. The maximum obviously will change because whatever that height is in meters will change because it's being multiplied by 100. So the only thing that will not change here of all these answer choices is the z-score, right? Once you standardize, it doesn't matter what you do to the data values in terms of adding all of them, adding a number to all of them, or multiplying a number for all of them. That's not going to change the standardized value, the z-score. All right, so 6 is E. Now, in that same vein, in number 7, it says we have students in a large site class measure the time in seconds it took each of them to perform a certain task. The times were later converted from seconds to minutes. If a student had a z-score of 1.72 before the conversion, what is the z-score after they changed the times from seconds to minutes? So in that same idea of what I just talked about in number 6, right? If you convert your data values, all right, it's not going to change your z-score. The z-scores are unchanged. So it's still going to be letter C, the same, 1.72. Okay, number 8. Now it says in this one, we have basically a 5-number summary plus our minimum and maximum, plus our mean and standard deviation, my bad. And it says that there was an error made in the reporting of the areas, and all of the areas of these homes in square footage should actually have been 100 square feet greater. So this one is a little different from 6 and 7, right? If you're just adding 100, that's only going to change measures of center. So measures of center will change, but measures of spread, right? Measures of spread are unchanged. And I'll show you, I'll prove it to you on one of these, okay? So if that's the case, when I look at my answer choices for which of these are the correct IQR and standard deviation, right? Both of those are measures of spread. IQR for interquartile range and standard deviation are measures of spread. So they are unchanged. So it should still be the standard deviation of 61.0723 and whatever Q3 minus Q1 is, right? Quartile 3 minus quartile 1. So I can look and do that math. That's 102. So actually the answer is A. Now let me show you, so I can prove to you why that's the case, right? If I take 1704 and add 100, then I'm going to have 1804. If I take 1806 and add 100, put it on top of it. So 1804. And then this one is 1906, right? So if you subtract 1906 minus 1804, you still get 102. So even though we've added 100 to all the different data values, right, measures of spread are unchanged. So that's kind of the main takeaway from the beginning of chapter 6. Is if you add or subtract all your data values to some number, right? If you take all your data values and add or subtract some constant, then measures of center will change, but measures of spread are unchanged. If you multiply your data values by some constant, or you divide your data values by a constant, then everything will change. Measures of center and measures of spread. All right, number 9. We have the weight of an adult male grizzly bear, saying that it's approximately normally distributed with mean of 500 and a standard deviation of 50 pounds. They're saying the weight of adult female grizzly bears is also normally distributed with a mean of 300 pounds and a standard deviation of 40 pounds. All right, so that's 2 normal models they're telling me about, right? They're telling me for the males, right? So for males, they've got a normal model of 500 with a standard deviation of 50. And for females, they've got a normal model with a mean of 300, standard deviation of 40. Okay? It says approximately what would be the weight of a female grizzly bear with the same standardized score, so z-score, as a male grizzly bear with a weight of 530 pounds. All right, so let's first standardize that male at 530 pounds. So I'm going to be using the formula y minus mu over sigma. So 530 pound male minus a 500 pound mean divided by a 50 pound standard deviation is going to be 30 over 50, so that's 0.6. All right, and then it's saying to take that 0.6 and make it the z-score for a female, right? So the same standardized z-score for the female. So, but now I need to find the weight for that female minus 300, right? Different model divided by 40. So this is something that we practiced together in class for chapter 6. So what I'm going to do is I'm going to go to Desmos, All right, you don't have to, right? You can just use your calculator, but I'll show you how I can go to Desmos and find what this y value is going to be. All right, so I'm going to go to Desmos, and I'm going to take my z-score of 0.6 and multiply it by, I believe it was 40. Confirm. It was 40, yes. And then I'm going to add 300. And that will isolate for my female weight of 324 pounds. So the female weight is 324 pounds. So my answer is B. Okay, number 10. Number 10 says the commuting time for a student to travel from home to a college campus is normally distributed with a mean of 30 minutes and a standard deviation of 5 minutes. Okay, if the student leaves home at 8:25 a.m., what's the likelihood, the probability that a student will arrive at the campus later than 9? All right, so again, I'm going to use my y minus mu over sigma. Now let's think about this. We're talking about later than 9, right? Later than 9 would need to be that our probability that our z-score is greater than, I'm going to find it, but greater than, before I standardize it, 35 minutes, right? 8:25 to 9 o'clock is 35 minutes. So when I standardize this, I'm going to use 35 as my data value. All right, so that's going to be 35 minus 30 is 5, divided by 5 is 1. So I'm going to find the probability that my z-score is greater than 1. So I have 1 here, and I'm shading to the right because it has to be later than 9 a.m. So later than that z-score of 1. All right, so I'm going to go to my z-score calculator, and it's going to spit out the answer for me here. Okay, so I'm shading to the right, and I'm telling the right z-score of 1, which is 15.87%. So I'm looking for my answer choice to be 15.87% or 0.1587. That's my answer. But when I look for my answer, I don't see it. So you always look for the closest one, which in this case is 0.16. Okay, let's keep going. Number 11. The distribution of these heights of these 6-year-old girls is approximately normally distributed. So we have normal distribution where the mean is 46 inches and the standard deviation is 2.7 inches. Okay, it says Aaliyah, I'm going to use A for Aaliyah, is 6 years old and her height is 0.96 standard deviations above the mean. So if I were to draw the curve, right, 0.96 is like right here, and that's where she is on the curve. All right, it says her friend Jane, so J, is also 6 years old, and it says her friend, or it says Jane, is the 93rd percentile. Now, we haven't really discussed 93rd percentile much. You might know what a percentile means, but what it means is that if I were to draw the z-score here for whatever it is, I don't know yet, and I were to shade below that z-score, right? So if I shade below that z-score, that means 93% is going to be to the left of Jane's z-score. All right, so that's what a percentile means. So like when you guys do standardized tests, you get a score report. I remember when I was in high school, I'd always look at that percentile as well, because if I knew that percentile was as close to 100 as possible, that means my score was better than so many other students out there, right? So the higher your percentile is, the much stronger your score would have been. All right, now it says, at what percentile is Aaliyah's height, and how does her height compare to Jane's? So we've got a couple of things we can do here to find the answer. The first thing I know I can do is I can find how much area is to the left of this z-score. All right, so I'm going to use my z-score calculator and find what percentile Aaliyah's height is. That's the first thing I can do with that z-score of 0.96. So this is to the left. I'm going to type 0.96. So her percentile is the 83rd.15 percentile. All right, so approximately the 83rd percentile. So immediately, I haven't done anything else besides find her percentile, and I can already narrow it down to D or E, because I know she's not in the 17th, 67th percentile. She's in the 83rd percentile. Now, you can do more work if you want, right? You can find the z-score for Jane if you'd like, but I know that Jane has to be taller because Jane is in a higher percentile, right? So the closer your percentile is to 100, right? In this case, the taller that girl would be, all right? So I know that the answer is D. Aaliyah is shorter than Jane, okay? If you wanted to do more work, you could find the z-score. I can go and show you the z-score. for Jane, all right, using the inverse, that Wolfram alpha link, her percentile was 93rd. So I'm going to type in 0.93, hit submit, and her z-score, again, to the left here, is going to be 1.476. So she's got a 1.476 z-score. So you can already see that her z-score is, all right, I forgot, 1.476, yeah. Her z-score is 1.476 standard deviations above the mean. So that's farther away, so that's taller, you're further to the right. If you wanted to go any further, might as well, right? We got this video going. I can find out what their actual heights are. This is completely unnecessary. Don't feel like you need to do this work, but I can just do it real quick, right, to solve for their corresponding heights if you wanted to actually see what their heights were. Okay, so I'm going to go to Desmos and multiply their z-scores by 2.7 and then add 46. All right, so we have 0.96 times 2.7 and then add 46. Oops, add 46. And then do the same thing, but 1.467, or no, it was a 476. 476 times 2.7 plus 46, and you'll see that the second one, right, so that's Jane, is taller by just over 1.5 inches, it looks like. Just over 1.5 inches, or just under, I should say, 1.5 inches taller than Aaliyah. Okay, again, that last part was not necessary, but if you wanted to do it, you could. Number 12, a distribution of scores is approximately normal. All right, so again, normal, with a mean of 78 and a standard deviation of 8.6. Which of the following equations can be used to find the score x, right? Some score x, I don't know what it is, that has above which 33% of the scores fall. All right, so there's 33% of the scores are above score x. So the first thing I'm going to do to find that score x is to find the z-score associated with 33% of the data values above it. So I'm going to go to that Wolfram again, and I'm going to type in 33%. Here we go. So I'm going to type in 33% or 0.33. Now be careful, this one I'm talking about going to the right. Okay, so we're talking about going above, so I'm going to put right tail. So I'm doing 0.44 is my z-score. So my z-score is 0.44. So if I'm using this formula of y minus mu over sigma, I'm trying to find the y value, the score associated with that z-score of 0.44. So this is what I'm looking for in my answer, right? It doesn't ask me to solve for it. It just says pick which one makes sense. Now you might be wondering why in the problem it says x and ours says y. The reason I choose y for you guys is because if you take upper level stats courses, it'll be more beneficial to write it with y. But again, x or y doesn't really matter right now. So the answer is D. Okay, let's keep going. 13. In a large set of data that are approximately normally distributed, all right, so again, another normal model, we have R has a z-score of -1. So draw my curve. There's the z-score is -1. Excellent. Then I have S is the value of the first quartile. Now, you might not remember this from our work in chapters 4 and 5, but the first quartile, right, if I were to draw that line, the first quartile has 25% of the data below it and 75% of the data above it. And I don't know that z-score. The next value is T, and it says T is the 20th percentile. So after our discussion about percentiles, that means there's 20% below that value for T. Okay? Now, right now I've got 2 out of 3 of them have percentiles, right? Even though this first or this middle one, S, said it was in the first quartile, that actually means the first quartile is the 25th percentile. T is the 20th percentile. So if I can find out how much area is below -1 when I have a z-score of -1, I should be able to find the percentile for R. So let's go ahead and use our z-score calculator right here and type into the left -1, which is approximately 16%. All right, so this one is the 16th percentile. So after our discussion about percentiles, remember, the higher the percentile is, the farther to the right it is. All right, so it'd be the greater value. So when it says to order them from least to greatest, the lowest one is R, right? That's the lowest percentile. Then it goes T, 20%, and then S. So the answer is R, T, S, which is B. All right, let's keep going. Number 14. The caffeine content of 8-ounce cans of a certain cola drink is approximately normally distributed, another normal model, with a mean of 33 milligrams. All right, I don't know. Does it say the standard deviation? It doesn't say it yet. A randomly selected 8-ounce can containing 35 milligrams has 1.2 standard deviations above the mean. So I could, if I wanted to, using my formula, right, I could actually find sigma because I have 1.2 standard deviations. I have 35 milligrams minus my mean. And so if I wanted to, I have one unknown, I could actually find sigma. But that's not what the problem says. It just says approximately what percent of cans of cola have a caffeine content greater than 35 milligrams. So guys, they've already given me the z-score. So I don't need to do any work to standardize. They already told me that z is 1.2. And it says greater than. All right, so I'm going to shade to the right. So all I need to do is go to my z-score calculator to find how much area under the curve is to the right of 1.2, that z-score. So right, 1.2, and it's 11.5%. So my answer is 11.5%. And when I look at my answer choices, the only one that makes sense is C, 12%. Okay, let's go to 15. Okay, so number 15. The school is having a contest in which the students guess the number of candies in a jar. All right, so they're giving us back-to-back stem plots. Now, as I told you in our notes in chapter 4 and 5, stem plots are not really that exciting. All right, yes, you can see the actual data values. All right, but most of the time we're going to deal with histograms. So I put this problem in here to show you that you can't just completely ignore them. All right, it says which of these statements is true about this distribution of guesses. Now, I'm just going to be honest with you. Most people mess this up. All right, it's not really their own fault. It's because it can get confusing. So I want to start with the female. I think the female one is the least confusing. If you were to think of this as a histogram, you would see that we have like kind of a main hump and then the tail. That's terrible. Try again. We have a main hump and then the tail goes on a little bit towards the lower numbers. So if you think about the 6 being on the left and the 14 over here, if my tail is going towards the 6, like in this one, that means it's skewed to the left. So the females are skewed left. All right. Now here's the deal with the males. A lot of students will tell me that the males are skewed to the right. But again, if you think of this as the 6 is the lowest, the 14 is the highest, you have more values near the 12, 13, 14, and less as you move to the 6. So that is also skewed left, right? The tail is moving to the left. So they're both skewed left. So if you look at the answer choices here, it says the distribution of guesses for both are skewed to the left, D. All right, a lot of students will end up putting that the females are skewed left. Which one is that? And the males are skewed to the right. A lot of students end up putting B because they forget that. That's the confusing thing. That's why I don't like back-to-back stem plots. It can be confusing when you're drawing the shapes. Okay? All right, 16. Oh, this one should be real fast. Which of the following statistics is defined as the 50th percentile? Okay, so again, you know we have the middle, right, is the median, which has 50% of the data above and 50% of the data below. All right, percentile means that it has 50% below that data value. Well, boom, there it is. The median has 50% of the data value below it. So the median is the 50th percentile. Quartile 1 is the 25th percentile, and quartile 3 is the 75th percentile, right? Because you have this is another 25. So you have 3 of these 25s that make up the 75th percentile for quarter 3. Okay, number 17. Okay, number 17 is analyzing side-by-side box plots. This is a really good one. Okay, it's saying which of these statements about the medians and the interquartile ranges are true. So let's just use a different color here to show you. Here's the median for the fertilized ones and the median for the unfertilized. And then the IQR, right, is the distance from quartile 3 to quartile 1, the edges of the box. Okay, so that's kind of make sure you know what median and IQR are correct. Okay, so number 17, all right, if I'm looking at this, it said the first one says the medians and the IQRs are the same. Well, you could hopefully clearly see that the median for the fertilized one is higher than the median for the unfertilized, so it can't be A. Okay, so the median for unfertilized is greater than the median for fertilized. No, that's the other way around. It should be the median for fertilized is greater, so that one can't be right. The median for the unfertilized and the fertilized is the same. No, we've already said it can't be the same. So just because of my understanding of medians, I've ruled out 3 of them. All right, now the D and E has the same first part. The median for the unfertilized trees is less than the median for fertilized. That's correct. So it's definitely D or E. And then now we have to figure out which one has the greater IQR. Well, when I look at the width of the boxes, the unfertilized width, right, this distance is wider or larger than the fertilized. So the unfertilized has a greater IQR than fertilized. So which one is going to get that? And the IQR is greater for unfertilized. So D is the answer. Okay, 18. All right, so 18 says another problem of comparing side-by-side box plots, this time horizontally. All right, we have a professor that gave the same test to 3 sections of stat students. On the 35-question test, the highest score is a 32. So you can see right up here, right there. For section 2, had the highest score of 32. Okay. Now for the lowest was 15, which is right there. So interesting. The lowest one was an outlier for section 2. Again, those outliers are by section. So even though 32 was not an outlier in section 2, it looks like 31, right, just in section 3 was an outlier for section 3. Based on the information displayed, which of the following is true? Okay, section 1 has the smallest IQR. So they're saying that section 1 has the thinnest box. Well, the thinnest box is actually section 2, right? You see here's quartile 1, here's quartile 3. That's actually the skinniest box. So section 1 doesn't have the smallest IQR. Section 2 does. Now, letter B. The lowest score in section 2 is higher than the highest score in either of the other sections. I don't understand why they put that as a choice. Maybe they're thinking because you're not going to look at the outliers, but I mean, this is a score in section 2, and that's the lowest score of all the sections. So it can't be higher than any scores, let alone the highest score in any section. Section 2 has the smallest range of scores. Again, they're banking on you forgetting about outliers. This is talking about range, right? That's highest minus lowest. So that's 32 minus 15. That's the biggest range, not the smallest range. That's the biggest range. All right, the top 25% of scores in section 2 are lower than the highest score in section 3. All right, let's see. The top 25% of scores in section 2, that's actually right here, this whisker, all right, are lower than the highest score in section 3. No, it actually looks like if it had said they're higher than the highest score in section 3 right here, then that would have been true because they're actually above the highest score in section 3. So it has to be E. Let's confirm. At least 50% of the scores in section 3. So it looks like this. The top 50% is this box and the whisker, this part of the box and the whisker, are higher than all the scores in section 1, which is right because the highest score in section 1 is only like right there. So yes, E is the only one that's correct. Okay, almost there. A few more. 19, another box plot. Data were collected on the number of text messages sent by each student in a large high school for one day. Here's the box plot. Based on the box plot, which of these is the most reasonable conclusion? All right, now, when you read this, there are going to be probably a lot of answers you think that are reasonable. Like letter A, where it says there are more students with data values below the median than there are students with data values above the median. But here's the deal, guys. What they're trying to do is they're trying to make you they're trying to confuse you about your understanding of box plots. Here is the median. Here's quartile 3. Here is, I'm sorry, not quartile 3, my bad, let me try again. Here's the median. Here's quartile 1. Here's quartile 3. Now, because it doesn't have any outliers, I know that the minimum looks like it's 0, and the maximum is just over 350, maybe 360, something around there. Okay? So in letter A, they're trying to get you to think that because the box is wider to the left of the median, that there's going to be somehow more values below the median than there are above. But guys, you know the median is right in the middle. There cannot be more values below than above. So that's why A is wrong. All right, they're trying to get you to look at the size of the box and how wide it is to the left of the median to confuse you. There are more students with data values between the first quartile and the median. So that's this distance. Then there are students with data values between the median and the third quartile. Again, they're trying to confuse you and say, oh, wow, it's so much longer between the first quartile and the median. But guys, you know that there's the same percentage of data values, right? There's 25% between the first quartile and the median, and there's 25% between the median and the third quartile. So another answer choice that will get a lot of students to pick it. There are fewer students with data values between the first quartile and the median than there are students with data values between the median and the third quartile. Just like in letter B, no, it's the same. All right, it's basically the same number. Okay, so letter D, there are approximately the same number of students with data values between the first quartile and the minimum. All right, yes, there's 25% of the data values there. And between the third quartile and the minimum, yes, there's 25% there. So that one is what I'm looking for. And the last question, or last answer choice, says the data are less spread out between the first quartile and the median than between the median and the third quartile. Again, right, they're talking about this as if you don't understand that there's the same amount of data values between them. Okay? All right. Let's go to 20. Almost there. 3 left. So we have 3 bags of candy, X, Y, and Z. Or excuse me, 3 brands of candy, and they're in different colors. Shayla buys 1 bag of each brand and counts the number of pieces for each color. So you can just think like M&Ms. All right, then she graphs them with a relative frequency distribution bar graph, and we have some statements. All right, now what gets confusing here is on these questions, they're going to try to have you compare between the different bars, right? And these are relative frequency in the x-axis. So that's percentages. So just be careful with that. For brand X, there were more green candy pieces than red. So let's look at brand X. So green is this one and red is that one. Well, it looks like there's 40% of the candies were red. And it looks like that's 30%, right? Because we're going to 0.7. So 0.4 to 0.7 is 30%. So actually, there's more red ones than green ones, not more green ones than red ones. So good try. Brand Y, there are more red ones than green ones. Well, let's see. Brand Y has a larger part of the bar is red than green. So that one actually, that looks good. Let's check C, D, and E. Okay, so when I look at C, D, and E, all of these answer choices are trying to compare brand X and Z, brand X and Y, and then brand Z with the other ones. The problem is, guys, is that we don't know how many candy pieces were in each brand. Okay, so I can't compare across brands here because I don't know if they have the same number of candy pieces in each bag. So that's why they're trying to trick you with C, D, and E. Like they'll try like, oh, look, the bar is bigger for that one, but you can't compare it to different brand letters. Okay, 21. The number of hurricanes reaching the east coast of the U.S. was recorded for each of the last 10 decades. Wow. And we have some summaries here. Which of the following statements is true? Now, this one is talking about outliers. So the moment I see that it's talking about outliers, I'm going to go ahead and find my fences. So the IQR is quartile 3 minus quartile 1, which is 18 minus 15. So 3. Then you remember that I'm going to take 1.5 and multiply it by that 3. All right, and that's going to give me 4.5. So my lower fence is going to be the first quartile minus 4.5, and my upper fence is the upper quartile, quartile 3, plus 4.5. So that's 15 minus 4.5 and 18 plus 4.5. So my lower fence is going to be 10.5, and my upper fence is 22.5. So if there are any data values that are below 10.5 or above 22.5, they are outliers. Well, my minimum is 12. 12 is not below 10.5. So I do not have any outliers that are below the lower fence. But I do have at least one outlier above the upper fence. 24 is above 22.5. So I have at least one outlier above that upper fence. Now I'm saying at least because I don't know the other data values, guys. I could have 5 data values that are 23, and those would all be outliers. So I don't want you to say that there's one outlier. Say there's at least one that's above the upper fence. Okay, so let's get some answer choices here. The smallest observation is an outlier. We already said it's not because it's not past the lower fence. Okay, this one could be true. The largest observation is 24. It's an outlier. That's true, but it says no other observations in the data set could be outliers. And I just told you that we can't claim right now that that's the only outlier because there could be other values that I don't know about. Like I said, the 23, that could be there, and it's also an outlier. We don't say C is right because both 12 and 24 are not outliers. 12 is not an outlier, so the only one is 24. So take a look at that sentence. 24 is an outlier, and it's possible that there are other outliers at the high end. That's true. Like I just said, there are no outliers at the low end. That is also true. So E is the answer for 21. Okay, last one. Almost there. So we have each person in a random sample of adults were asked how many DVDs they own. Man, this is getting pretty old, pretty dated. I'm not sure how many people even have DVDs anymore. So we have summary statistics are given below. Which of the following is true? Now, the first thing I noticed, and there's a lot going on here, all right? You've got N, which you haven't really talked about that. That's just how many people were asked in this sample. So 117 adults answered the sample. We have a mean, all right? We have a median. Don't worry about this, that TR mean. Don't worry about that. We know standard deviation. Don't need to worry about that yet. You know minimum. We know maximum. So there are people that don't own any. Well, somebody owns 3,000 DVDs. Whoa. Here's the first quartile. Here's the third quartile. Okay. Now, when I look at this, all right, yes, I see that 3,000 is really high. Okay. And it doesn't have any questions. Well, it looks like it does. So I might as well do some outlier work here. But the first thing I notice is the mean is much higher than the median. All right. And that makes sense to me because this maximum of 3,000 is going to pull that mean towards it. So let's do some outlier work. All right. The IQR is quartile 3 minus quartile 1, which is 95 minus 30, which is 65. I'm going to multiply 1.5 times 65. Let me get that number for you. 1.5 times 65 is 97.5. And then I have my lower fence, which is going to be 30 minus 97.5, and my upper fence, which is 95 plus 97.5. Now, when you do this, I don't know if we've done one of these yet, but in the lower fence, you'll notice it's a negative number, right? 30 minus 97.5 is negative 67.5. We can't have any data values below negatives, all right? So I cannot have any outliers in the low side. But my upper side, right, is going to be, when you add these together, you get 192.5. And we definitely have at least one outlier, right? 3,000 is way higher than 192.5. So I know there's at least one outlier. So let's go and cross out E, because this one says there's an outlier on both the low and high side. We know there's not one on the low side. For the first one, 75% of the adults in the sample own more than 95 DVDs. So that's incorrect. It's close, but it's incorrect because they're saying, right, there's the median, there's quartile 3, and they're saying 75% of the adults own more than this, right? 95 is quartile 3. It's actually 25% of the adults own more than 95. So that's why A is wrong. It should say 25% if that were to be true. 50% of the adults in the sample own between 0 and 129.4 DVDs. I don't know any way that I could possibly know if that's true. That's 0 in the mean. That's not, statistically, that tells me that's not a thing, okay? C, the distribution of the number of DVDs owned appears to be approximately symmetric. One of the key things about symmetric or approximately symmetric distributions is the mean and the median should be roughly the same. And as we've already discussed, the mean is not near the median. It's much higher because of that 3,000. So I would imagine if it's going to show any shape, it probably shows some skewness to the right. So that one's wrong. And so the only one that is correct is that the IQR is 65, which we already calculated. All right. So I know this was long, so go ahead and try to watch it in chunks, and good luck on your test.